All right, we're rolling now. On to effect size. Probably about, God, it must have been 30 years or ago now. Researchers were urged within psychology, even formally, to present what's called an effect size estimate alongside probability values. That is, don't just tell us whether we could reject the null hypothesis or not. Tell us something about the magnitude of the relationship in a way that's comparable across different studies. That's what the effect size is getting at. It's the magnitude of the relationship. How big is the difference between our two means? Now, there's some aspect of that when we have a t-test. We are looking at the difference between the two means. However, when we're doing a t-test, when we're doing that t-test, the denominator of the t-test is affected by the sample size. So bigger sample sizes make for a smaller denominator, making a bigger t-value. That means that that t-value is always a product of not just the difference between the means, but also a product of the size of the sample. There's a statistic called Cohens D, also known as a standardized mean difference, that addresses differences in terms of standard deviation units. You can see the formula is relatively simple. It's just the difference between the means over the pooled standard deviation. And what it gives us a value that is in units of standard deviation, in standard deviation units. And you might also notice that this gives us a value that's basically a z-score. What does this tell us? This tells us that there's a 0.42 standard deviation difference between the two groups. Why it's important to express this in terms of the standard deviations is that when we divide by standard deviation, we have standardized our units. And what that means is I can go to another study that uses a different manipulation and get a sense of where my effect was relevant to that, to the other study. These are directly comparable values. The APA publication manual, I hope that you all have a copy of this. You will be hurting for certain when it comes to do your thesis and it comes to get approval from me as the graduate coordinator, and you haven't adhered to APA style, and you have to do that all in the day or two that you have left before the deadline. So definitely pick up a copy, get the copy with the spiral binding so the pages don't fall out. Within the APA manual, I don't have the exact page number because my version 7 is in my office and I haven't been there since March. For the reader to appreciate the magnitude or importance of a study's findings, it's almost always necessary, always, to include some measure of effect size. Now, you'll notice in this class, I will rarely say always, because always doesn't cut it in statistics. There's always exceptions to always rules. However, always, there's no exception here. Always include that effect size. Just as a note, and we'll see some of these values a little bit later in the semester, there are a number of different types of effect sizes, and you can see some of them, probably ones that you're familiar with, D and R from correlation, eta squared or partial eta squared from analysis of variance, R squared from regression and multiple regression. Lots and lots of different effect sizes along with Cohens D. The only point that I want to make here is that these are all on different metrics. So you always want to specify the effect size that you're using and recognize that, 0.10 might mean very different things for a D statistic versus, say, an eta squared statistic. They're on completely different scales. All right, sizes of the effects. It's not uncommon to see authors reference the size of the effect using small, medium, and large labels. I use those small, medium, and large labels in this table. And the reason why I did that is just for comparative purposes, just to show that they're on different scales. Otherwise, I would say, otherwise I probably would not use that. For example, for the D statistic, 0.2 is small, 0.5 is medium, 0.8 is large. Now, a lot of people latch onto this and want to use this. So again, a lot of authors will regularly use these benchmarks. One of the reasons is that these were part of all of the original writings on effect size. Even though you will see this in the research literature, don't do this. If you have a D value of 0.4, say, oh, well, that's almost medium. No, don't interpret effect sizes that way. It is stupid to do that. This completely and utterly ignores the context of the statistic. Anytime there's, like a benchmark or a guide that says, oh, this, if this, then this, it's probably going to be wrong. You really have to understand the context of different effects. An effect size of 0.4 is pretty typical for social psychology, but it might be really, really large for something like neuroscience. It might be really small for something like cognitive. So again, don't use small, medium, and large terms. These are not shirts. They don't get those sorts of sizing labels. So, as those of you who've had a class with me or two with me before know, some things set me off and I go on rants. So here's the first one, everybody. Effect sizes. Again, effect sizes aren't shirt sizes. Typically, effect sizes vary wildly from field to field. Cognitive psychology will generally tend to have bigger effect sizes because they're using highly controlled experiments, bigger than, say, compared to what you might find in neuroscience. That's just part of the methodology and how things are constructed. Small effects also can be extremely important depending on the context. A famous example here, there was a large-scale study, this happened in the UK, and it was studying the relationship between heart attacks and aspirin use. Now, as you may or may not know, aspirin is very widely prescribed as a preventative medicine to avoid heart attacks. They actually ended this study early because it was so clear that it would be unethical to continue the study and not give the people in the control group aspirin because they were dying at higher rates. What was the size of the effect? Well, it was roughly D of 0.03. That wouldn't even scratch the surface or get anywhere close to what we call a small effect. That D value, it corresponds practically to about 3 fewer deaths out of every 100 people, though. So clearly that is a very important result. So when you convert this to real world terms, pretty valuable. There's another contextual consideration here that may or may not be available for interpretations of other sorts of effects. In the aspirin study, it's good to think about the cost of the treatment. Aspirin costs now about a penny a day. Clearly, there's a lot of benefit there for very little cost. Now, if the drug were more expensive, if you were talking about something that cost $200 a day and we had an effect size of 0.03, we would probably say, no, the cost of this doesn't justify the benefit. But here, when we look at the cost versus the benefit, we see a substantial benefit. So big point there, context is really important in these interpretations.